So let me introduce our speaker here today, Dr. Stephen Greybush, who's coming to us from Penn State University, where he's an associate professor there in the Department of Meteorology and Atmospheric Sciences. Stephen's also affiliated, I should mention, with the Institute of Computational and Data Sciences. And he's also the associate director for the Center of Advanced Data Assimilation and Predictability Techniques there at Penn State. And then just to complete the list, he's also a member of the Consortium for Planetary and Exoplanetary Sciences and Technology. So a little bit of background, Stephen got his bachelor's in meteorology at Penn State. Then he went to the University of Maryland to work with Dr. Eugenia Calme, who's well known in data simulation, and got his master's and PhD there. Stephen's background is quite diverse. Overarching, he uses numerical simulation, data simulation, machine learning to basically understand a whole variety of phenomena, ranging from winter storms to convective initiation, and then even dust storms on Mars. And so and today we're going to get a little bit of a treat, a little bit different for us, learning a little bit about Mars. I thought it'd be something different, but sort of a blast from the past because some of you don't know this, but our division used to be called the Institute for Terrestrial and Planetary Atmospheres. And when I arrived way back when, we actually had planetary faculty. Jane Fox was on the faculty and so forth. So we have a history in doing some planetary work here in this division. But there is a Mars group at Earth and Space Sciences who Stephen got to meet, one or two faculty. They work on Mars there in ESS. So that was, I think, nice to coordinate that. So today we're going to learn a little bit about Mars. So take it away, Stephen.
Thanks so much, Brian. It's great to be here. Stony Brook. This is the department, and great to share my research with you all. So for here, I'd like to thank also all the people that have made this work possible, especially numerous students who have worked on the Mars projects in the past with me, as well as collaborators, my advisor Eugenia Calme at Maryland, John Wilson and others at NASA Ames, folks from the Jet Propulsion Laboratory, as well as several other places.
So Stephen, your microphone turn on. There's a little button. You're pretty loud, but it's on the top. Just look that button. Yeah.
All right. So let's get started then for today. So just by way of introduction. So in addition to the Mars work that we'll be hearing about, I wanted to give a little bit of an overview about what we do at Penn State, especially in the ADAPT Center that I'm part of. So my overall themes are the data simulation, numerical weather prediction, and ensembles. How do we forecast and improve those forecasts? How do we improve our dynamical understanding of our model simulations? How do we combine them with observations to do a better job at understanding that? I've done work with Lake Effect Snow. We've looked at East Coast winter storms. We're part of the NASA impacts team along with Brian. We're studying East Coast winter storms that have big impacts here, as I know. Severe thunderstorms, tropical cyclones, some idealized modeling work, induced complexity models, even some coupled Earth system models, hydrology, public health, and Mars, which is what we'll focus on today. So comparing Mars and the Earth, we'll want to get a sense of the basics first of the Mars weather and climate. And then what we'll do is we'll look at creating a Mars reanalysis. So just like the Earth reanalyses that many of you may work with, we're trying to reconstruct the past of Mars weather using observations and models. And then finally, we'll use that reanalysis to explore science questions. What are the traveling weather systems of Mars like? What about dust storms? Finally, the polar vortex and water ice clouds. So we'll start with the basics. This is the relative size between Mars and Earth. We can see that Mars has a similar length of day, 24 hours and 39 minutes. Those working in early missions would have Mars watches. That way you get an extra 39 minutes of sleep each night. You'd have twice the length of a year for the Mars atmosphere. And we have a similar axial tilt. So this is going to apply. We do have seasons on Mars. And the primary atmospheric constituent is carbon dioxide. But the pressures are significantly lower than that of the Earth, around 6 millibars. So that's going to have a huge difference in the atmospheric circulation and features. So taking a look at Mars seasonality, since we don't have a Mars calendar as of yet, we think of seasonality in terms of the solar longitude, or LSODES. So LSODES starts at 0 for the spring equinox, and LS90 for the summer solstice, and around to the other seasons of Mars. And Mars is closest to the sun at the perihelion, about LS250 during its winter. And we also notice that Mars's orbit is much more elliptical than the Earth's, 44%. So therefore, there's going to be more of a contrast between the hemispheres, simply based on the orbital geometry of Mars, as well as some other features that we'll see in a moment. So how do we know what we know about Mars? Okay, so we had a spacecraft that had been sent to the red planet, starting with the Mariner program in the 1960s. And from the Mariner program, we first observed dust storms. Early images of Mars just saw a red haze rather than the features of the surface. Right? Once that dust storm cleared, we were finally able to get sharper images of Mars and see it's very different than, of course, the Earth and the Moon. We see the canyon systems and the topography. And then from there, we also then sent the Viking landers, which sent barometers to the surface of Mars. And we're able to get a sense of Martian weather. Right? Weather systems moving by the lander every few days had the associated rise and fall in surface pressure. We also then sent the Mars Global Surveyor, the TESS and instrument on board, which is used by some of your colleagues in geography to study the geology of Mars. And TESS is going to be used as well as Mars Climate Sounder. Here in this presentation, it'll look at the Martian atmosphere. So whereas my focus is primarily on orbiter missions, because I'm looking at the global weather of Mars, many of the attention in the media and other scientific studies is looking at the geology and looking at Mars in the past. Could it have ever supported life? And so some of those missions, from the Mars Pathfinder, the Mars Exploration Rovers, the Phoenix mission, and to the more recent Curiosity and Insight and Perseverance rovers. Okay, so some of these do also have weather stations, and we use those weather stations to help be an independent validation for some of our simulations and reanalysis. So we also learned more about dust storms and other features of the Martian weather, which we'll talk about a little bit later. So here is a view of Martian topography. So this is from Google Mars. You can actually go there and zoom in on features of interest from Google Mars. And from this, we can see that the northern hemisphere is much lower in elevation, about 5 kilometers lower, and much flatter. It is hypothesized that this could have been an ocean in ancient Mars history. So from here, we can see that there is topography, perhaps a wave number 3 across the northern hemisphere. That's going to play a difference in the traveling weather systems and their modification by terrain. We see the Valles Marineris Canyon system, as well as Olympus Mons, which is 3 times taller than Mount Everest. Okay? The southern hemisphere terrain is much higher, much more cratered than the northern hemisphere. So what are the main features of Martian weather? So you'll find many things in common for that of the Earth. So there's traveling weather systems, our Rossby waves, our cold fronts and warm fronts. Those familiar features are found in Mars, and that's going to be a main point of the study in a moment. We have thermal tides. So while we do have weaker versions of thermal tides on Mars, on the Earth, the Martian thermal tides are fairly dominant. And these can change day-night temperatures from 80 Kelvin near the surface, and these modes propagate through the atmosphere, having impacts on the wind field, the pressure field, and other aspects. We do have water ice clouds, so we see them present here in this visible image. They're usually found around terrain, although there is an aphelion cloud belt throughout much of the tropics. From here, we actually had precipitation, snowfall detected by a LiDAR from the Phoenix mission in the polar regions, about 70 degrees north. We have surface frosts and fogs, and we have polar ice caps. So there's a permanent ice cap of water ice in the northern hemisphere, as well as a seasonal cap of CO2 ice. This is where about a 1/5 of the atmosphere actually freezes to the surface, whether through direct deposition or CO2 snow. So this is a pretty noticeable feature of Mars, and we can see this across this image at the bottom. Okay. We have dust devils. This is a view of a dust devil. These can be much taller than the Earth counterparts, sometimes reaching several kilometers in height. So these, if anyone saw the movie The Martian, were depicted kind of at a later point in the movie. And we also have dust storms. So without revealing too much about The Martian's plot for anyone that still wants to see it, we do have dust storms. They do cloud up the sky and kind of darken the surface. They do have strong winds, but do remember that the surface pressures on Mars are 6 millibars. So keep that in mind about an important plot point at the beginning of The Martian and its scientific validity. So regional and global dust storms are definitely important for mission operations, as we'll learn. Okay, so looking across the scales for Mars, you can see spanning kind of turbulence and dust devils at the small scale to the topographic flows and tides at the period of about a day, to the traveling weather systems and the regional dust storms. And then finally, these global dust storms stand out in the fact that they can last for months and they occur every few Martian years. Why they occur every few years is one of the mysteries that we're working to solve, but there are a number of hypotheses as to that. So for dust storms, this is first a view of Mars in normal conditions. We can see all the way down to the surface features, different craters and mountain features and other features as well. But when we have a dust storm, most of the atmosphere is obscured in a thick dust haze that we can see here.
Where is that taken from?
This is taken from, this is a NASA figure, and you can either stitch together individual spacecraft views for Mars, or you can use Earth-based telescopes to see dust storms. So we have a
That was sort of more my question. Is it from Earth-based telescope or from orbiters?
Yeah, most of what I'll show today is from orbiters. This particular view, I'm not sure if it was a stitched together or a Earth-based telescope, but we definitely have a record even pre-spacecraft era to get some sense of dust storms on Mars going back further from Earth. And so this 2 to 3 years almost reminds a little bit of ENSO on the Earth. It's a phenomenon that's not regular. It's every few years. And there's probably some dynamical mechanism that we partially understand, but perhaps not fully understand as to when the next ENSO event will occur. Okay, so here's the impact on the surface mission. So before, when I saw The Martian and saw the skies getting dark, I wasn't sure would the opacity really become that intense, but actually Opportunity measured a opacity of 11. So at this point, Opportunity was actually designed to last only 90 days on the Martian surface. Dust was accumulating on the solar panels, which would eventually reduce its power. But thankfully, dust devils would come by and blow off the dust from the panels and let it last about 10 years. But at this point, we get to a global dust storm, which Opportunity was in an unfortunate location for. This reduced the power so much that Opportunity shut down, and unfortunately, Opportunity did not survive the storm. So we have a robotic casualty on Mars from dust storms. So we're going to return to that storm in our simulations. So we'll come back to that storm in a little bit. But let's talk about how we do now our Mars reanalysis. So the key parts of this are going to be spacecraft observations, a global climate model, data assimilation, which bridges those two, and then finally the validation techniques at the end. So observation side, we have polar orbiting satellites or spacecraft, and each of these are our IR sounder. So looking in the infrared, thermal emission spectrometer was designed to primarily look at geological features, but also you can look in the CO2 bands to infer atmospheric temperature. Test profiles and retrievals extend to about 40 kilometers in altitude. And we see as far as spatial coverage a 2 a.m. and 2 p.m. orbit. And at first glance, that seems sparse by Earth standards. But then we could look to the success of the 20th century reanalysis at reconstructing weather in the early 1900s based only on surface pressure observations. And then Mars Climate Sounder was designed to look specifically in the limb through the atmosphere at a slant path. And then from that, you can get vertical profiles all the way up to 80 kilometers, much greater vertical resolution. But with the challenge that when you're looking at a slant path, that can be opaque when you have a dust storm and you might not always see down to the surface. So we're going to take these observations and we're going to try to combine them now with a Mars global climate model developed by John Wilson, one of our collaborators. So this climate model we're running at coarse resolution, 5x6 on Mars, that's about 300 kilometers. So synoptic scale features only, although the model can run down to 1/8 of a degree. 28 vertical levels in the atmosphere following the terrain, then turning over to pressure levels aloft. We have a gaseous and condensed CO2 cycle. So we are representing the changes in surface pressure due to CO2 ice caps each year. We have IR scheme that includes dust radiative feedback, as well as the radiative impacts of clouds. We have soil model, boundary layer scheme, water budget, gravity wave drag parameterizations, wise cloud microphysics. right? So a lot of the things you'd see in an Earth GCM needed to be adapted for Mars, right? We don't currently have a CO2 ice microphysics, but that's something that's perhaps on the way in the next few years. And then we have tracers for dust, water vapor, and water ice. So we get a sense for a dust storm. If dust is lifted somewhere, where will the winds transport that dust, and so forth. And dust lifting and sedimentation can be turned in the model as well. Okay, so what does the Martian diurnal cycle look like? So this is the extreme day to night temperature contrasts, right? Could be 80 to 100 Kelvin at the surface, right? And extreme contrast also from the surface itself, going up into even, let's say, 2 meters above the surface, where the rover might measure. You can see temperatures might be an autumn day in Stony Brook at some point 2 meters above, right? And especially at the surface, you might be especially actually up to maybe even a nice autumn day. Right? But at night, you're 100 degrees Celsius below zero, potentially. Okay. So this is, tongue of warm air is going to be following the subsolar point, moving across Mars, and this is what's going to initiate the thermal tides that are in response to this heating. You can get a sense for what a time series of temperature and pressure look like. Right? From the thermal tides, we don't just get a single diurnal cycle, but we also get a semi-diurnal tide, as well as Kelvin waves that are initiated. And there's actually some higher order harmonics as well that are initiated. So the thermal tides are a fairly big feature of Mars. So if you want to study Rossby waves and weather systems, you need to filter out the thermal tides to really zoom in on those particular features. But of course, the real winds in the atmosphere are the superposition of all these different modes. So if we were watching that surface temperature signal, primarily following the diurnal tide, whereas the surface pressure signal is following components of both the diurnal and semi-diurnal tides. And looking at a seasonal cycle, we can see from the rovers that this is variations from 900 pascals to 720 pascals, right? And we said that's because the atmosphere is freezing to the seasonal cap. So that kind of dominates the signal. Right? You can see at some periods of time, there's more let's say interdaily variability than others, right? So weather matters in some parts of the year more than others. Now these rovers here, many of them are in the tropics where you actually get more of the transient eddy or weather system activity in the mid-latitudes. So the next part would be looking at the seasonal cycle. So first of all, this would look familiar to those with Earth. Right? Warm near the equator, cold near the poles, getting colder aloft. And then westerly jets in kind of the mid-latitude regions due to thermal wind balance. Okay, what looks a bit different than the Earth is if we look at the winter solstice. So this is height, basically, the pressure, and latitude. So in this case, right, we have a smaller planet. We don't have the mitigating influences of oceans. We have a very thin atmosphere, and so it heats up very quickly. So you actually get the warmest point here near the poles in the summer, as far as the diurnally average temperature. So that's going to spawn a global Hadley circulation with a descending branch in this up at the winter pole and leads to that polar warming phenomena that you see here aloft. Okay? And you can see that one dominant kind of westerly jet in the winter hemisphere. So now that we understand a little bit about what models and observations can show, how do we combine those together? So data assimilation is the science of combining models and observations to see what the best state of the atmosphere we can get, and therefore to better allow for more accurate forecasts in the future as well. And so it includes a few things. First of all, we don't just want to directly insert observations. We want to know that observations also have errors. So we need to consider both observation error and errors in our background or our data assimilation system, right? And weight those two sources of information accordingly. Okay, the next part is that we don't have observations everywhere. So we need to interpolate and we need to spread that information, I should say, in space. And we do that using background error covariances to fill in the gaps where we don't have observations. Then finally, we use the dynamical model to allow that information to move forward in time. Imagine that if we saw that there was a dust storm and we assimilated dust, then the model winds would move that dust over the next hour forecast, and then we would start our next cycle with that updated information. So in this case, we're using an ensemble of simulations. We do that to represent the uncertainty in the model by having both initial condition differences as well as differences in the radiative forcing for Mars. Okay, so we do this assimilation every 1 hour actually in our most recent version. And we do this with 16 Ensemble members. So at the end, we get a reanalysis project. And what does that reanalysis look like? It's going to be an hourly product of temperature, wind, surface pressure, and aerosol for about 8 Martian years, which is about 16 Earth years. Okay. So at any hour for Mars in the last few decades, we'll know exactly, we'll know a representation of the atmosphere in many different fields that is constrained by observations and filled in the gaps by the modeling side. Okay. Because we're doing the ensemble, we have that uncertainty estimate. And we also have a control run simulation. So we could look at the differences both with and without the assimilation. So in what ways did the observations help to better constrain the atmosphere? And we did this with both the thermal emission spectrometer and Mars climate sounder spacecraft observations. Okay, so this reanalysis is publicly available. So you can download .cdf files just like you'd work with Earth data sets. And those in the Mars community are using this for various studies. So how do we know the accuracy of such reanalysis? So we can evaluate it in a few different ways. Right? First, we can compare it to the freely running model by itself and see if they're different and are different reanalyses more similar to each other versus freely running models. Okay? If we don't have many independent observations, we can run a short-term forecast and look at the skill of that short-term forecast. Right? Now, it's not as good as a fully independent observation, but it is that those new observations, let's say 6 hours later, are ones we have not yet assimilated. And then what else we can do, there are some independent observations, including from radio science profiles on Mars, that have not been assimilated at all and are fully independent observing systems that we can compare to. So looking at reanalysis intercomparison, one was done by collaborator Darren Waugh, who looked at 2 different Mars reanalyses. So the first one was the MACTA reanalysis from the UK. It was not an ensemble reanalysis, but uses a completely different modeling and assimilation system. And we then compared to Mars climate sounder observations, which were not assimilated here. And we were both able to get a better fit, and even including in the upper atmosphere where the TESS observations were not found. Okay. And then we found where are the locations where the larger disagreements. Well, the cap edge baroclinic zones, we have very strong temperature gradients. That's a more challenging region. And there's also been some comparisons to radio science, which I don't believe I show here, but showed that there are improvements from between the free run and the reanalysis compared to these independent profiles. But beyond just kind of these root mean error statistics, we like to look at specific features of the Mars atmosphere to see how well we're doing. So we explored them in a series of papers from the zonal mean circulation to the thermal tides in the atmosphere, to the polar vortex. So Mars does have a polar vortex, which I'll show a little bit later, to the atmospheric aerosol, to transient eddies, which I'll focus a bit on, dust storms, and water cycle. And we see a synergy between data assimilation and that world and the feature-based scientific study of these phenomena. Right? If we see that we're either representing or not representing a particular feature well, we think, how do we improve our data assimilation system or our model to better represent that feature, and then reiterate? Or what new improved techniques can we do to better represent those features? So we'll start here next with these science questions. So this is a view from the Curiosity rover looking at Mars with Mount Sharp in the background. Okay, and there's somewhere on here, there is a weather sensor. Right? We can measure wind and temperature on Curiosity as well as barometric pressure. Okay? And the first of these is going to deal with these transient eddies. Okay, so this is what a Mars weather map might look like. These are temperature eddies in the color here. The black lines are isobars. The gray lines are, so these would be low pressure areas. This would be high pressure areas. And then we also have the wind. So let's just make sure we got, so we can see here we're in the northern hemisphere. So we'd expect a cyclonic counterclockwise circulation around our low pressure. And we do see that. Right? So this would be familiar with those that are looking at Earth weather maps. Okay, so these are predominantly in the mid latitudes. So, but you do see some signatures of the eddies reaching down to the tropics. So that Curiosity rover that I showed in the last slide does measure weaker versions of these weather systems as they pass over the lander site. Okay, but Viking 2, which is in the mid latitudes, gets a much stronger view of these weather features. So here's another view now of all of Mars. It's not big weather map, right? You can get a sense of kind of the extent of these weather systems heading down into the tropics. Right now, this is LS-219, so this is late northern hemisphere autumn. That's why the northern hemisphere is more active at this time. But the southern hemisphere also has its time of year of active waves. Right? These waves are more active when we have a strong temperature gradient, right? Think baroclinic instability. If you have an ice cap of CO2, its critical temperature is 150 Kelvin. Right? And then if you imagine the sun is heating the bare rock just south of that, that is a natural temperature gradient that's going to provide baroclinic energy for these waves. Okay. We typically see wave numbers 1 to 3 on Mars. It's a smaller planet than the Earth, similar Rossby radius of deformation. And we can get a sense for these waves. They would be generally moving west to east across the northern hemisphere if I were able to animate that. So we can also look at the wave propagation through a Hofmahler diagram. So this is longitude across the x-axis, this is time across the y-axis. So imagine here, if I'm starting in the part of the diagram, I see a positive temperature anomaly that then propagates eastward over time, eventually crossing Mars in about a span of 5 LF, which is about 10 days. So why do I have these three diagrams? Well, one of them right here on the right is the Mars model alone. So you can see this has a much more regular wave train. And predominantly wave number 2, but some other periods are wave number 1 and 3. And so waves on Mars, you notice, propagate at the same speed despite the different wave numbers. Wave 3 is actually much shallower, wave 2 a little deeper, and wave 1 even deeper still. Now these are the two reanalyses. So if you're looking at these, you can imagine that EMARS and MACDA look more like each other than the model running by itself. Okay, so that gives us some confidence that we're actually representing the weather on Mars in a reasonable way. They're not perfect, there's some disagreements, but we can quantify kind of that these two are better than the agreement with the Mars model by itself. Okay, so we want to ask how well can we constrain eddies, right? We have some success here with that. Okay, so what else can we do? We can also look at traveling waves and think about the seasonal and interannual variability. Okay, so now this is a plot of seasonal, this is LS, and latitude. Okay, so this is where are the waves strongest at what times of year in the northern hemisphere. Okay, so wave 1, we can see that once you get into the northern hemisphere autumn, there's strong wave activity. There's then a solstitial pause in the middle of the winter, right? Similar to what we experience on Earth in the North Pacific, right? And then going into the spring, we see the wave activity pick up again. Okay, and then these are looking at amplitude of wave number 1, 2, and 3. What's perhaps more unique on Mars is that particular seasons favor the particular wave number to dominate. So this time period right here of LS 225 seems to favor wave number 3. Interestingly enough, that time period is also a favorite period for regional dust storms. Right? So there's a link between these traveling weather systems that have the winds that lift dust and then kind of the dust storms that then propagate across the planet, as we'll see in later slides. These wave 3 eddies can be very shallow and are linked to baroclinic instabilities that we revealed with a Hubble vector analysis. Okay, so we can now look at several different seasons. Okay, so here's the interannual variability from 3 different Mars years. Okay, these are from the TESS era. These are from the Mars Climate Sounder era. Okay, so we're seeing similar seasonality, but differences in amplitude. So even though Mars Climate Sounder has more vertical resolution, it struggles sometimes to see the very shallowest waves in the atmosphere since it's looking through more atmosphere on that limb path. So we're looking at ways to use radiances to better constrain the eddies with Mars Climate Sounder. Yeah. So it's good when you're thinking about interannual variability to know if there's systematic differences in the observing system that might matter. It's not that Mars atmosphere suddenly changed between these 3 years to the other 3 years. So we can also look at the traveling wave activity by wave number. And here's that wave 3. Okay, that seems to dominate at this time of year. And you get a sense of the interannual variabilities by doing studies like this. Okay, so how do we summarize this across many years? So this is a diagram that has a number of different Mars years. And then the color tells us what wave number we're working with. Okay, so wave 1 is blue, 2 is green, 3 is red. And then these two lines together are two different reanalyses. So we're trying to look where the similarities or differences in wave regime. Again, definitely some areas of disagreement, but where did the strong agreements come out? If we look at it, LS 225, there's quite a number of years where both reanalyses are saying wave 3. Is one of them wave 3? And then looking down at later in the year, wave 3, wave 3. Again, that's that season of that's popular for regional dust storms. So what would now it's transitioning from the traveling waves over to dust storms, what would it look like if we took a synoptic weather map and put it over a visible image? So this is from the orbiter. So this is an image that was stitched together from multiple polar orbit passes in the visible. And then this is the reanalysis fields on top. So it all looks dusty because Mars's surface is dusty. But if you look for some of the differences in texture, this right here is an area of dust that's being lifted. Okay? It has kind of that fuzzy convective type texture to it, contrasted with the surface. And right along here, our reanalysis is showing winds. Right? So that's kind of a way looking forward is how much do we trust the reanalysis that we can match to actual dust fields and then use that reanalysis to study dust storms in particular. And so that's what we would work toward if there was kind of an operational product from Mars, something like that. Okay, so let's think about dust storms. So dust storms do form along frontal structures. You can see one right here. Right? You can imagine if we have cold fronts in Mars, we're going to have kind of strong winds along the cold front. They're going to lift dust from the surface. It's challenging compared to the Earth, right? On Earth, there's maybe limited areas we could lift dust from. Mars, the whole surface is pretty much dusty, but some areas have more dust available for lifting than others. So how do these regional dust storms look like? So this is an example from the TESS era that shows a storm starting in the northern hemisphere. So this is that time of year that I mentioned where that wave 3 was prominent. And what was special about the wave 3 is that the wave 3 can sometimes have a superposition with the diurnal tide signals. So if you have the enhanced wind from a traveling weather system along the tidal winds, right, you're going to get an even stronger wind adding those together. So then that wind can sometimes initiate these storms and get them to move south across the equator into the southern hemisphere. So that at that point, we're starting to lose our Earth analogy, right? We don't necessarily, at least the troposphere, have an analogy of a storm starting in one hemisphere, moving clearly across to another hemisphere. Okay, so this is an example of a regional dust storm. These are opacities, maybe a tau of about 2 in the visible. And these are storms that can last several days to maybe a week or so. These storms happen every year on Mars, right? They're not exactly repeatable, right? There's definitely interannual variability, but they're favored at certain times of year. Okay, so this would be typical Martian extreme weather, but it's not yet the global dust storm. Okay, so this storm took that path starting in the northern hemisphere, heading toward the southern hemisphere. Keep that in mind because this storm just lasted several days and then fizzled out. But the global dust storm that we'll come to later did not, right? It developed into a global storm. So that's, again, a big research challenge. What was different between those two cases? Was it that one storm was a little bit stronger and was able to take off? Was there something different about how dust was distributed around the surface of the planet? Right? What was different between those two instances? Okay, so let's look at an interannual record of dust amounts. Okay, so this is LS, so we're looking at seasonal index for a whole year. This is latitude. The color bar is looking at amount of dust at 7 different Mars years. So this is that storm we just looked at. This is just showing up in the red register here. This is a global dust storm. And you can see how that's saturating the color bar and lasting for several months. Okay? And that interannual variability, Mars year 25. Here's another one in Mars year 28. The next one waited till Mars year 34. And now we're still kind of waiting. So Mars year 34 is 2018. We'll see when the next storm happens. And that gives you a rough sense of the interannual variability of these storms. Okay, so what does this look like? Here's the Curiosity rover. Here's Opportunity. Here's the storm, and this is an animation courtesy of NASA. This is stitched together views from orbit and highlighting kind of areas of dust. So the storm originates here, moves south, and then you see, let's say when it starts early, watch the dust at the beginning, kind of start to circle the planet. We just specifically wrote a paper on what mechanisms allowed the dust to circle Mars so quickly. But what really helps the storm, even some of the regional storms get a little bit of that transport. What really becomes key for global storms is that multiple lifting centers at different parts of the planet start to get triggered. And then when you have multiple lifting centers, then they really start to accumulate dust in the atmosphere, and then you start a positive feedback cycle at some point until there's significant dust and the baroclinic energy activity dies down and the storms start to weaken. But then even once the storm activity is weakened, the dust is suspended in the atmosphere, right? So you don't necessarily have to have active winds blowing for multiple months. It just takes a while for the atmospheric capacities to get back to something more normal. Yeah. So we saw opportunity. Opportunity gets hit early and hard. So that led to kind of the failure of opportunity solar power that we talked about earlier. It was an unlucky position. Plus, Curiosity was nuclear powered, so it didn't need to worry about its solar panels. So we studied that storm back in 2018. I remember my grad student Hart looking at the storm early in cycle and kind of was just making an informal prediction. This looks like it might go global, and it did, and became a big weather maker for Mars. So his paper looked at how do you actually get the dust that was lifted low in the atmosphere in the northern tropics to actually circle Mars. And so the number of parts that were part of that pathway, right? First, the Hadley circulation, bringing the dust equatorward. This is around the equinox, right? So the vertical part of the Hadley circulation is going to be close to the equator at this time, right? And the dust is actually going to be moving day to night. Right? In the daytime, it's heating and it gains buoyancy. So it actually gets lifted during the daytime and then sinks at night a little bit. So that's what kind of the dotted line is telling us. But gradually it's getting lifted up in the Hadley circulation. And then this is also expanding and contracting day to night, but gets entrained into the zonal jet. And from the zonal jet, this gets transported around the planet. So that's a schematic diagram. We can get a sense for what this looks like in some model fields. Okay, so this is dust in the nighttime. See concentrated 0 to 30 north. That's the location where the storm was happening. Okay, we see here are the V winds, the U winds, and the vertical winds, the W winds. Okay, so I'm just going to go back between day and night. Notice how the dust gets transported upward and outward between these two plots. Okay. And we can see actually the huge differences in day to night V wind aloft, right? I talked about thermal tides. Thermal tides get even stronger during dust storm conditions. And so how can we know whether these winds are transporting the dust? Well, we put particle tracers into the model. We started them off in the location where the storm was. We used all our different ensemble members to represent uncertainty. And then after a few days, right, we start to see this is latitude. You start to see those dust particles moving across Mars and eventually encircle it. Okay. And we can also get a sense for how they move from near the surface to go higher in the atmosphere as well. Okay. So our paper kind of deals with this dust transport issue during the storm. Okay. We also wanted to get a sense of, we see dust moving across Mars. How do we know that that's dust being transported rather than being lifted locally in other parts of Mars? Right. So we actually saw that they both processes were contributing to that, probably in maybe roughly equal magnitudes, right? Based on our modeling study of advection versus then kind of the residual would then therefore need to be lifting. So in addition to the dynamical features we talked about, Mars also has a polar vortex. Okay, so this is looking first at zonal min, okay, at pressure and latitude. Okay. And from here, we can also plot the Ertel potential vorticity, right? We can see this event potential vorticity maxima here associated with our jet and our temperature gradient along the pole. Okay, so one important question for Mars is water vapor is moving between different poles. And we want to get a sense of how porous is this polar vortex for water transport. That's going to matter not just for the atmosphere, but perhaps even for the studies of geology and other processes. Okay, so we did some comparisons of observations, our reanalyses in the model free run with the Mars Climate Sounder, and we're looking specifically at water transport. So in this next slide, okay, we're going to think about some of the significance of the water transport. Right, so water we see on Mars both in the water ice clouds, but also water vapor. Okay, how much water are we talking about? A few precipitable microns, right? But it is enough though to allow us to form cirrus clouds, which have a radiative impact of maybe 10 to 20 Kelvin, right? And over time, if there's gradual transport between the northern hemisphere and southern hemisphere, right? That's important to long-term studies of Mars between these reservoirs. And transport also leads us to interesting questions about the polar vortex and the different components of the flow. Okay, so here, specifically noting in the northern hemisphere winter, looking at the zonal mean structure, which I showed in that last slide a little bit. The paper goes a lot more detail. Okay, and then how do these Mars climate sounder observations influence water transport? And what physical mechanisms connect these and are different between the free run and the reanalysis? And so this is a complex figure. There's a lot being plotted, but I'll try to guide you through it. So first of all, the color is temperature. So right in here, you see change of color very quickly. This is the temperature gradient that you see near the edge of the polar vortex. Okay, what else is plotted here? We have meridional stream function, solid black for positive. Okay, so here's the stream function, right, giving us a view at the extent of the Hadley circulation. Here's the stream function. So we might also want to get a sense of, does the stream function cross the polar vortex flow? Okay, in the free run, not so much. In the reanalysis, there are some streamlines that do cross the polar vortex. What else is plotted here? We have water vapor in red contours. So we can see that there's a lot more water vapor here outside the polar vortex than inside. And this is very water vapor poor. So any transport across is going to make a huge difference here and rapidly lead to clouds because it's very cold, as you can see in the polar vortex. So even these small amount of moisture can change the cloud very quickly. And then finally, water ice clouds are the white clouds. And so in the reanalysis, we see that the clouds are much thicker than in the free run. And the good news is that matches more closely the Mars climate sounder cloud profile observations, which we did not assimilate. Okay? So that's one, this is a complex study, but that's one piece of evidence that we think that the transport is better represented in the reanalysis compared to the free run. So another question we could ask about Mars is if we were to do numerical weather prediction, how far into the future could we forecast? All right, so this is a retrospective study rather than a real-time study, but this is starting out from the reanalysis. This is imagining if we keep assimilating observations every hour, we have about the skill level of 4 degrees Kelvin on average compared to observations that we haven't yet assimilated. So then if we run the model without any assimilation, we start out with an error of maybe 7 or 8 Kelvin. Okay? If we launch a forecast from our reanalysis, how long does it take for the skill to degrade to that of the free run? Okay? So in this, it's showing maybe 3 to 5 days of forecast skill. Okay? But this is in some ways a simplistic view. It's encouraging, but simplistic. One is that on Mars, the derivative time scale is an order of magnitude shorter than for Earth. Instead of being about 10 days, it's about 1 day. So if you don't have the dust and water ice clouds in the right place, your model basically has climate drift very quickly. And it's going to have the wrong kind of even zonal mean temperatures. Okay? So depending where you're looking, that might be the dominant process leading to forecast error rather than the kind of the chaotic growth of errors in initial conditions. But in the mid-latitudes, the initial condition errors are going to be the important part. The good part is the weather regimes, or the waves, transition more slowly between different wave regimes than the Earth. So perhaps they're a little bit more predictable than the Earth. Okay, so we have a number of things going on if we're thinking about forecast accuracy. So if we were to better improve forecasts, what other observations could we consider? So there's a new Emirates Mars mission that actually has a very different orbit than the polar orbits from the Mars Global Surveyor and Mars Reconnaissance Orbiter. So this mission, when it's very far away from Mars, almost gets a hemispheric view. So it's almost as if there's test instruments looking at a wide swath of Mars. So from there, this is another scientist in the Mars community, Roland Young, who's assimilated these. We're going to be also assimilating these EMARS observations. And from here, you instead of just getting these 2 a.m., 2 p.m. or 3 a.m., 3 p.m. observations, you'll see across many local times. So we think that has a lot of promise. What else do we think could help in future missions? I'd love to see more surface pressure stations, preferably in the mid-latitudes. Right? Perhaps wind measurements from Mars could be very interesting. And so there is a Mars community. It's pretty small compared to the Earth community, but kind of looking at, there is actually even a Mars data simulation community. So there was a meeting in France about 5 years ago. This is maybe about the extent of those interested in Mars data simulation. It's more than just me, but maybe an order of a dozen or so. Okay, and then there's even those looking at Venus data assimilation in Japan that have successfully assimilated Venus observations. And then the Mars atmosphere community is about maybe 200 people around the world. Right, the geology community is much larger compared to Mars atmosphere, but that gives a sense for kind of that this is a small community, but it is more than just a handful of people looking at these problems. Okay. So finally, what about weather on Mars? So I just checked this morning, I think as of October, maybe 7th was their last observation, and there was a high of 0 degrees and a low of -100. So you get a sense of how this changed from this last report here. Right, so not so bad in the daytime, but you would need to take shelter at night. So at that point, I will thank you all for listening to the seminar and kind of a recap, kind of what we learned, right? Comparing the reanalysis to new observations. Let's just validate our reanalysis. And these can be used for initial and boundary conditions for other models. We eventually want to work with new maybe parameterizations and other ways to do data assimilation. And also we're thinking more ways to do aerosol. So the Mars Climate Sounder gives vertical profiles of aerosol. Right now, we're only using the column information. So we want to look at assimilating vertical profiles. We know there's challenges with that as well, but that's kind of an exciting area to look at, as well as radiances. Right now, we're just working with the retrieved products, but the radiances might let us look further down into the atmosphere where there's maybe less of a good constraint in the retrieval, or that it cuts off when it's opaque in certain channels. And continuing understanding transport, dust storms, and a lot of other interesting questions. So again, thanks so much for the opportunity to speak here and visit.
Hey, thank you, Stephen. That's yeah, Edmund.
Yeah, I think you in one of the slides you showed that the reanalysis, the waves in the reanalysis actually are much less regular than what's the model simulation show. So are there hypotheses why that's the case?
Yeah, so first, John, the model that we've used here, John always thought that there was a systematic model error and that it was too regular in this wave too. And so there could be something in the modeling side. Another part, when you do assimilation, you're going to be forcing a model field with observations that are incomplete in space and time. So you can almost think, well, naturally, you'd expect it to look less regular because you're kind of pushing it toward observations in certain areas. But I think what's happening is the real Mars atmosphere in some ways does have more variability in wave regime. Why that's the case, I think, is a more deep question that we'd like to explore. Why, like this, even compared to Earth, this is maybe seems somewhat regular, perhaps. Right, but why? I think that's where we have to really get into the theory and the dynamics, and I think that would be an interesting question to further explore.
Just kind of building on that while we're here. I mean, they're so regular where they're long lasting.
Yes. Mm-hmm.
So these waves don't go through some wave breaking or type of, what we see on Earth, where you'll get wave amplification and breaking and stuff like that. So does that happen, or it just seems so long lasting and maybe not as
I'm gonna go
growing?
The amplitudes are more fixed as they move around. Oh, I shouldn't say fixed because I want to show a topography slide here. It's somewhere in here we go. Okay, so this is looking at Lee cyclogenesis and topographic modulation of waves. So you can see the topography, 1, 2, 3. So this is the amplitude of the red vectors, but if we look at eddy amplitude, this by itself, you'd see a similar thing. So you do see that aspect of the waves where they're kind of being amplified and weakening as they interact with the terrain. So that is happening. But as far as kind of, let's say, imagine like an extratropical cyclone rapidly deepening, right, and then maybe dissipating and reforming, that is, I do not see that as much on Mars. Now, maybe the observation systems are not as sophisticated. I'll look carefully at the EMARS observations now that you have more than that once a day coverage. But at least from the modeling point of view, there seems to be more regularity and less of kind of those starting from like a zonal mean, you get a rapid development of a wave. But we do know from like dust storms and things that you do have some type of development, but it seems less of a noticeable feature in the Mars atmosphere than from what we've seen so far.
It's interesting. Yeah, hang on.
Yeah, so given the low density of the atmosphere, even near the surface, and the abundance of dust. In the equation for the density, do you include the dust in the pressure gradient force?
I don't think we do. So we do definitely need to account for many things that are different. So our ideal gas constant, of course, will be different. We can need to consider the different atmospheric composition. Dust, I'm going to talk to the others in the market. I have not seen that used directly in the density. We just represent dust as tracers, and we track how much mass, and we can do other calculations for the opacity units or density units for dust. But we almost separate we have basically the dry atmosphere and then our tracer fields and consider them
Like
separate.
in the Earth's atmosphere.
Yes.
Yes, I would imagine that it matters to the dust scheme. How dust would be, say, ejected from the surface.
Yeah, so for the surface, so right now for this assimilation project, what we do is we have an observed dust opacity. Where there's a mismatch between the two, we then inject dust in the boundary layer as a proxy for lifting, so that we're getting it at the right place. And then the model ejects the dust. The model can do self-lifting, meaning if the winds are strong enough past the critical threshold, like the Ganot and other formulations for Earth climate models, you can turn on interactive lifting, but we don't yet trust that we'll have the details of the wind field enough that for the reanalysis, we trust the wind to lift dust. We want to instead have the dust appear to match observations and be transported. So those equations would be similar to the Earth, where you have a critical threshold, you need to know how much dust availability is there, and things like that. So that is one feature that you can use in the model for dust.
Thank
Yeah,
you.
thank you. Yeah, Levi.
I have a couple questions that maybe I'll focus on two. One is, are there any important impacts to heating or cooling of the atmosphere due to the phase change of CO2?
Yeah, so what we do is in our modeling system, because we don't yet have the microphysics for CO2, when it gets to the critical temperature, we know that the atmosphere won't get colder because it's the main constituent. So you would keep in a real atmosphere, right, turning the CO2 ice, that would have latent heating, and your temperature is not going to drop below that, significantly below that temperature. A little bit below, yes, if you have microphysics. Okay, but then how do we represent that? We take that amount of mass out of that part of the atmosphere, we put it onto the surface. And therefore, then the latent heating is essentially by keeping that atmospheric temperature at that critical temperature. So that's kind of a less sophisticated way of modeling than if you had kind of a real CO2 ice microphysics. But either way, that kind of is preventing in the polar vortex the temperature from getting any colder than it does. Here's apply here. So you're almost you look at the pole and you were asking what is the critical point for CO2. You probably just follow this column in here, so be close to those temperatures in Kelvin. So it stops the atmosphere from cooling further because at that point you have latent heating from the phase change.
Okay. I don't think I fully understand that, but maybe we could talk more at lunch about it.
Sure.
It seems like if you so you have this GCM and you have topography, and there's this idea that in the distant past there was northern hemispheric ocean. Has anybody filled up the ocean with water and seen what kind of a climate you get? Because that'd be kind of fun.
There are paleo-Mars modelers. So
with like a lot of water where there's a huge ocean.
I believe so. So I know they've done different stages. So there's kind of more recent past, let's say millions of years ago versus billions of years ago for when that ocean might have been there. I know there's modeling both in the 1D, so trying to see what different atmospheric constituents would need to be in the atmosphere to support those temperature ranges. I believe there are 3D GCMs, but I'd want to double check to confirm to point you in that direction for
I
that.
mean, this one seems like it'd be great. This is a three-dimensional primitive equation GCM, right?
It is, yes.
So maybe you could get a graduate student to just fill up the ocean.
Yeah. So there are out at NASA AIM, there are some, I think grad students or maybe postdocs, maybe that's a better postdoc project, who are looking into that. I think Catherine Stakely was looking specifically at some of the CO2 issues as well as kind of ancient Mars at NASA AIM.
Jackson, you had your hand up.
Yeah, I have my hand up. So I'm curious about I may have missed this, but is there a like a seasonal aspect of when the global dust storms are initiated? And does that coincide when the Hadley cell is strong enough to like move the dust in its own little jet?
There is a seasonality, so. You notice there's almost never dust storms in this time of year, right? You can think also where Mars is in its orbit, it's closer to the perihelion. So that maybe could be providing more energy to the system that way. At this point, LS 180 was for the Mars 25 and 34 storm. This one was maybe a little more unusual at LS 270. So it seems to be this time of year, but you don't see many starting when that time when the regional storms are peaking. So maybe there is something to that about dust being able to, like the different strength and configuration of the Hadley cell and other things that helps things to go global at that time versus other times of year. Might be something to that.
Yeah, lots of interesting questions about dust. The first one that you said sort of the lifetime of a dust storm is about a week or something like that. And I would think the fall velocity of dust particles must be a lot faster there than it is here. And you must be taking that into account. I'm kind of curious how you generate dust. Is it just proportional to wind speed, or is it got some kind of turbulence issue associated with it? You had the dust devil in there. Can you make that?
Yeah. Okay, so great question. So first of all, the dust devils, since we aren't modeling down at the large eddy simulation scale, we have there's a convective parameterization you can turn on in the model that would be kind of the net effect of this if many dust devils are working. So there's probably some that are maybe doing that really fine scale simulation that look specifically at that. Then from the global dust storm point of view, so you were thinking about the storm, so the interactive wind field lifting the dust, that's an option in the model, but not one we use here. So remind me again the first part of the question. I want to circle back to that. Sizes, right?
I was asking deposition rate. I'm not sure what order. Deposition rate, generation issues, lifetimes.
Okay. So for what we can do with Mars dust, we have multiple tracer schemes. You can pick how many tracers you want. We usually use 3, a 0.1 micron one, which has a very low fall speed. It's almost indefinitely suspended, but maybe on the time scale of months. Then you have I believe a 1 and a 2.5 micron. Now, of course, there's a continuum, but we thought it would be representative of 3 different size bins that might be important to model. So of course, the larger the dust, the faster the fall speed. Those large dust particles might be important in saltation and lifting, and then just gets lifted up for a little bit and eventually settle down. So it's nice to have multiple sizes. There's some, you can think of, there might be more sophisticated ways to model dust that's more a continuum rather than particular tracers. Other groups have looked at that, but that's kind of how we simplify it enough so that we can compare to observations and kind of reduce it to that a reasonable amount of complexity that's realistic enough to that there's multiple sizes, but not so complex, then it would be kind of an under-constrained problem of how do you compare observations, and once you have an observation, how do you update? Let's say if you had 20 different sizes, it wouldn't be maybe constrained enough on how to map to those.
Well, I think that's a reasonable approach, but I guess the question is, to what extent the lifetime of the dust storm is influenced by deposition versus regeneration?
That is a great question. So for the global storms, dust being suspended high in the atmosphere, so the vertical transport can actually take dust up to 60 kilometers of Mars. So at that point, if these are fine particles, that could be one reason why it takes so long for the background dust levels to return to normal, like in this case. Now, in the dynamic time scale, there I'm thinking that the winds and the kind of actual lifting processes and dynamics might be more important than the amount of time that dust is suspended. But that's something actually I think I'd like to think further about. Does that time scale a significant limit, or is there enough winds that are constantly relifting dust that maybe it doesn't matter as much? That if the initial parcels maybe fell in a few days, if the winds, the dynamics are still present, that gives rise to that lifting, then it becomes less important.
So yeah, lots of great questions. Thank you.
Okay. Before we do the last one, I just want to mention, if you're online, if you have a question, just type it in the chat since we can't hear you, and then we'll try and get you at the very end. Kamazima.
So I'm gonna go back to dust.
Sure.
So because the aerosols are so important, And you showed some mountain. What's the connection between the volcanic activity with the amount your dust budget?
Okay, so I'm gonna go to the topography plot here. Okay, so dust sources. Topography can matter a bit. This Hellas Basin is a lower depression in the surface of Mars. There's a lot of dust activity around this basin. And sometimes when the northern storms come down into this area, it could either be maybe additional wind enhancement from the flows with the topography, or perhaps there's dust that's more readily available for lifting in this region that could be interesting for spawning a storm. So I think you can think of topography as in a few ways. First, it's what it does with the flow. But then second, almost thinking of the geographic features of Mars that some might have more dust available for lifting. It's different. I'm thinking like on Earth, like dry lake beds can be a big source for lifting in dust storms. So whereas Mars, maybe there'd be ancient dry lake beds, but there might be other features of Mars that, whether it's like craters that have accumulated dust, or maybe all the smaller storms accumulated dust in one area, and then when you get strong winds, it's finally able to lift that dust. But I think that you can think of those type of features, like dust availability features, as another way that the terrain kind of matters for the dust storms.
But for volcanic activity doesn't, like from volcanoes, that doesn't affect.
Right. So on Mars, Olympus, all the volcanic activity is currently dormant. So in ancient Mars, that could have been the case. And I know there's some that have actually used, I think, ancient Mars models to see where volcanic debris and other kind of geological features might be dispersed. But on contemporary Mars, since the dormant, it would more be kind of those indirect effects.
Okay, well, let's move on to lunch. So we kind of discussed with Stephen there, the students. Yeah, please meet with him.
Anything in the chat?
Right after Matt, right after lunch. I don't see any, so that's why I moved on. So lunch and meeting with the students. Let's thank Stephen again for